Hello students, and welcome to topic 12 of alternative and renewable energy sources. The topic we will be covering is passive solar. In passive solar building design, windows, walls, and floors are made to collect, store, and distribute solar energy in the form of heat in the winter and reject solar heat in the summer. Here is a view of a passive solar home. Design can be said to be extreme. Passive solar buildings do not need to look extreme. Their design can look conventional. It is only necessary to pay attention to the details, window location, overhangs, thermal mass, etc. Orienting the building correctly with respect to the sun is step number 1. This shows the importance of window location and overhang. The overhang must allow the sun to enter the windows in the winter time, but block the sun and not allow the sun to enter the window in the summertime. We will look at 3 categories of passive solar systems: direct gain, indirect gain, and isolated gain. Direct gain is the most popular type of passive solar system in architecture. In a direct gain structure, solar energy is transmitted through the south-facing glazing. This approach works best when the south window area is double glazed and the building has considerable mass in the form of concrete floors, masonry walls, insulated on the outside. The direct gain system will utilize 60 to 75% of the sun's energy striking the windows. Indirect gain is a system where the storage mass collects and stores heat directly from the sun, then transfers heat to the living space. The sun's rays do not travel through the occupied space to reach the storage mass. There are several indirect gain passive solar systems such as mass wall, water wall, roof pond. The indirect gain system will utilize 30 to 45% of the sun's energy striking the glass adjoining the thermal mass. Thermal mass or mass wall. This figure shows a concrete wall used as a solar collector and heat storage device. When sunlight strikes the rough blackened surface, the concrete becomes warm and heats the air in the space between the wall and the glass. Some of the solar heat is carried off by the air, which rises and enters the room, but a large portion of the heat migrates slowly through the concrete. With good exterior insulation, such concrete wall collectors can be sized to maintain comfort for 2 or 3 days of sunless weather. Water wall is an even better heat storage medium than concrete. A cubic foot of water can store 62 BTUs for 1 degree Fahrenheit temperature rise, while the same volume of concrete can only store 32 BTUs. The convection currents in water rapidly transfer the solar heat from the collection surface to the rest of the volume of water and thence the rooms. Consequently, the water wall lose less heat to the outdoors and are more efficient collectors of solar energy than concrete walls. Roof pond. Containers of water on a roof of a house can also be used to collect and store the sun's energy. The solar energy collected with a roof pond system is radiated directly in the rooms below. Very even heating occurs, and water temperature as low as 70 degrees Fahrenheit can still be used to heat the house. However, roof pond collectors have a number of drawbacks. As the sun is low on the horizon during winter, the daily insolation on a horizontal surface is least when it is most needed. Therefore, roof pond collectors are much better suited to lower latitudes, those between 35 degrees south and 35 degrees north. At these altitudes, the sun climbs up higher in the sky on a winter day, and snow buildup is not a threat. Also, the roof ponds are extremely well suited to the purpose of summer cooling. Isolated gain is a system has an integral part separate from the main living area of the house. Examples are sunroom and a convection loop through an air collector to a storage system in the house. The ability to isolate the system from the primary living space is a point of distinction of this type of system. The isolated gain system will utilize 15 to 30% of the sunlight striking the glazing toward heating the adjoining living space. Solar energy is also retained in the sunroom itself. Passive solar systems generally possess 5 components: a collector or aperture, an absorber, thermal mass, distribution system, and a control system. Windows have performance ratings. The U factor tells how good the window is at insulating out the outdoor temperatures. The lower the number, the better the window insulates. The insulating value is indicated by the R value, which is the inverse of the U factor. The U factor is included in the energy performance rating label offered by the National Fenestration Rating Council. Solar heat gain coefficient. The solar heat gain coefficient, also called the shading coefficient, is a measure of how well a window transmits or reflects heat from the sun. The lower the coefficient, the better a window is at blocking the sun's heat. Windows in hot or temperate climates should have a low solar heat gain coefficient. South-facing windows in cold climates should have a high solar heat gain coefficient. Visible transmittance is the percentage of visible light that is transmitted through the window. Air leakage is a CFM, cubic foot per minute, infiltration per square foot of window. This slide depicts solar heat gain coefficient. Low asymmetry windows. Window glass is by nature highly thermal emissive. To improve thermal efficiency, insulating properties, thin film coatings are applied. These coatings reflect radiant infrared energy, thus tending to keep radiant heat on the same side of the glass from which it originated, while letting visible light pass. This results in more efficient window because radiant heat originating from indoors in the winter is reflected back inside, while infrared heat radiation from the suns during the summer is reflected away, keeping it cooler inside. Low E is depicted here. The thermal radiation is reflected. This depicts how the overhang can block the sun in the summertime and allow the sun through the window in the wintertime. The absorber, as shown here, collects and stores the solar radiation. Absorbers have a high thermal mass. Thermal mass is a material that has the capacity to absorb, store, and release the sun's heat energy. Its density and levels of conductivity help to keep the internal temperature of a building stable. Objects that have thermal mass have inherent qualities for both heating and cooling. This shows how a particular thermal mass can work, storing the energy and then releasing it. There must be some means of distributing the stored energy throughout the home. The control system is a method by which solar heat circulates from the collection and storage points to different areas in the house. A strictly passive design will use the three natural heat transfer modes: conduction, convection, and radiation exclusively. In some applications, however, fans, ducts, and blowers may help with the distribution of heat through the house. Roof overhangs can be used to shade the aperture area during the summer months. Other elements to control under and/or overheating include electronic sensing devices such as differential thermostats that signal a fan to turn on, operable vents and dampers that allow or restrict heat flow, low emissivity blinds, and awnings. The 5 elements are shown here. Daylighting is the practice of placing windows or other openings and reflective surfaces so that during the day, natural light provides effective internal lighting. Particular attention is given to daylighting while designing a building when the aim is to maximize visual comfort or to reduce energy use. Here is an example of windows providing daylighting. If there's any questions, please post them on eLearn Help Discussion.